So in short, I'm going to be squeezing 14 weeks of teaching into just 20 minutes. So I hope I'll manage, and I'm going to try to make it also accessible to non-technical people. So I'll do my best. And I'm talking in these things because I think there are people from the future who are also listening. So let me go ahead. So first, I'll start with the realization that relational tables are actually thousands of years old, 4,000 of years old. This is a relational database, what you see right here. And that was on a clay tablet. It actually contains a lot of complex math in there, but this is just to see, to show you that tables are something that everybody understands, and they've been understood for thousands of years already. So now, if we go a bit forward in time, and especially into the 1960s, then what you notice that people have been doing is they stored their files directly on their drive as files and directories, and then they had to code in some programming language in order to access the files. Except that in 1970, there was a revolution, and in fact, to me, it's the beginning of database history. Somebody called Edgar Code had the realization that this is not okay to just have to access the files and deal with physical details. And so he had the idea that since everybody understands what a table is, even without any degree in computer science, we should just expose to a table, as a table, to the end user, the data, and have this high-level way of interacting with the data. All the physical details are hidden. And this is called data independence, and it's been with us for now 15 years. And as you know, relational databases are quite successful because I don't think there's a single company that doesn't have them today. Then a bit later, there was an evolution because of the scale-up, because then we had so much data that didn't fit into tables anymore, and that was even growing too fast. So there's a few other technologies, key-value stores, triple stores, column stores, document stores that started popping up. You wouldn't believe it, but key-value stores, that was the blockchain 15 years ago. Everybody wanted a key-value store for anything. All right. So when we talk about big data in large scales, because I would like to actually bring you there to even petabytes of data, we speak a lot about the 3 V's. And V means volume, variety, velocity. So I'm going to go in turn through each one of these to give you an intuition how they play together and how this will impact the future development of XBRL, at least if we want to continue to scale with all the reports that will appear in the future. So I'm going to start with the volume. So just to give you an idea of the scales, you probably know that the Earth's circumference is roughly 40,000 kilometers. It's round on purpose. That was kind of made that way, defined that way. Now if you take a larger scales, we are already at the petameter when we talk about the solar system. It's already a prefix that not everybody knows, especially associated with meters. And if I go all the way to the entire visible universe, because there might be even more than that, but at least what we see, we are at, if we consider it's 13.8 billion years, we are at 138 iota meter. And actually, because of the expansion, it's even more than that. But until recently, the iota was the highest prefix that we knew, but it seems that we run out of them. So now there's Rona and Quetta that appeared. So we keep having more and more and more of them. Just to say that in terms of computers, we basically went all the way from our size to Jupiter in just a few decades, to the petabyte, exabytes now that starts to be accessible in the data centers. So that's for volume. Now the second V is variety, and that's about data shapes. What I like to teach my students is that there are 5 fundamental data shapes: unstructured data, graphs, trees, tables, and cubes. And that's pretty much it. Almost any data model you can imagine falls into one of these 5 fundamental data shapes. Then you can define data models based on that. But this is the spirit of data independence. If you understand that the data should be seen on a high level like this to the user, you can build the entire system hiding the physical implementation. So now just talking a little bit of this in the context of XBRL, then if you look at filings that you can open in some interactive view, so this is an example coming from the US, from Edgar, you can see that this almost looks like a spreadsheet, right? And this is pretty much what this is. And now things seem to be going in the direction that we are going to have files just like Excel or Word files, but we are going to have I just invented that XBRX. I don't know how it's going to be called, but basically we're going to have a file that we can open in some piece of software and then interact with it. And that's actually quite recent because the report package specification is just a few weeks old. Yay, that's a step in the right direction. And hopefully that will hide all of the XML and the complexity of this. Because what you want is to have something visual, right? So first you could view it as something that is called the facts table that looks like this, where you have all of the dimensions and then it's called the measure actually in data warehousing, the actual value. This is not any table. This is a very particular kind of table that is in fact associated with data cubes, as I will show you. So it's not any relational table. But if you actually look at an entire report with thousands, up to 10,000 facts, then this is more like something sparse like this. The reason why it's sparse is that you shouldn't actually be looking at this from the perspective of a single big fact table. Instead, you should be looking at it as components, as you know, the balance sheet, income statement, the cash flow statements, all the notes and so on, right? So this is the first thing I expect that any XBRL processing software or at least user interface is or will be doing to separate this in this way. And then what's important, again, as I said, even though it can be viewed as a fact table, this is actually a cube. It's a cube. The only reason why we look at it as a table is that we humans see well in 2 dimensions, but as soon as there's 3, 4, or 10 dimensions, we are less good at that. Right? But in fact, it's a cube. It's very, very important to understand this. Or a hypercube if you want to sound fancy. And so the idea is that we have these dimensions here. I took an example with concept, period, entity, which are 3-dimensional coordinates that give you that one value, 10,000, right? There can be more than 3. The user can define their own dimensions or axes, as they can be called. And then in terms of user interface, what we have is something that also is very well known in data warehousing, in the beautiful world of data cubes or OLAP. It's the notion of slicing and dicing. So the idea is that you take these cubes and then you start manipulating them with something that is often called an algebra in the context of databases. Slicing means we take a specific company, a specific currency. Dicing means we put it on rows and columns, right? So here I put the concepts on the rows and the period on the columns, but of course you can do the opposite and it works just as well. And here I want to say table link bases, yay, because this is pretty much what table link bases get right. Not just, so they are used explicitly in for example, for CoRep FinRep, but even in the open taxonomy architecture which is based on presentation networks, we still have this idea of this visualization, right? Even if the table link base is not used explicitly, the idea of slicing dicing is still here. And so you can view the presentation network in the case of the Edgar filings or IFRS or SF filing. The presentation network kind of gives you this model of which concept you have, the hierarchy of concepts, all of the dimensions and so on. Then you can display this quite nicely actually with these L shapes that represent the aggregations all the way to the domain. And then everything, and that's the spirit of data independence, everything that is at the XML level, even the notion of a link base, the notion of arcs and edges, the notion of presentation network, definition network, the notion of having facts in XML, all of that is hidden or should be hidden or will hopefully become hidden. Because if you look at calculations, it doesn't matter that we have a calculation network in XML. It really doesn't matter. What matters is that visually we see that some numbers sum up to some other numbers, right? So right now, what we already have is the one that is vertical. I hear that the one that is horizontal might appear soon as calculations 2.0, as I learned was pushed by the IFRS Foundation. All right. Then another network is another kind of link base is the definition link base. But again, who cares that it's an XML file with edges and arcs, right? What matters with the definition link base is we're doing validation. We are saying it is allowed to have a value in that cell, or it's not allowed to have a value in that other cell, right? This is what it's really about. So visually, it's like painting some cells in gray to say that nothing should go in. Then we have the labels, which is yet another XML file with arcs and edges. But again, who cares that we have arcs and edges connecting labels? What we care about is in a user interface, the user can select a language. Here I put some Schweizerdeutsch. I don't know if we have Swiss German speakers. I did my best because it's only a spoken language. I'm not supposed to write that down, but if you look at the small print, then maybe you will discover some of it. So it's just the idea that you can swap the language, but again, data independence, that's how it feels like to the user. So the idea, if I wrap up on that part, is that whatever data shape you have, here it was cubes, right? But for every shape, cubes, tables, trees, graphs, or unstructured, you have some things that you can do with them. Cubes, you can slice, dice, aggregate, roll up, pivot, cross-tabulate, and so on. Tables, you can select, project, group, and so on. That's the relational algebra, and so on, right? As soon as you understand these 5 data shapes and the fact that they are on a high level separated from the physical layer, you're 80% of the way. And in the bunch of text now, we could almost add the large language models, which kind of took that over. All right, now moving on to scaling up. The idea of data independence is that we have a data model, in that case data cubes with XBRL and some language used to querying it. But all of that is implemented on top of a physical layer. So until now, or at least until the years 2000s, we had everything on a single machine. We had a relational database on a single machine with a single processor, and it would all be implemented maybe in C++. But the user would see tables and maybe interact with SQL or software that supports it visually. But then what happened in the 2000s is that we slowly migrated to several computers, in fact, tens of thousands of machines in a data center. There are some in Zurich, in the north of Zurich. They are not in the Alps, by the way. A lot of people think it's the military bunkers in the Alps. But we have a lot in Zurich. There is this ring around Zurich. And it's up to 10,000 of machines. The reason for that it's not more than that is because of the cooling and the energy. It's as much as an airport, really. So we cannot really push it beyond that. Then you need new data centers if you want more. So let me say a few words about that. Why we need all these machines. So the idea is that if we look at the evolution of how we store data, we can look at 3 things. The first one is capacity. How much data can we fit on a hard drive, for example? The second one is how fast can I read from the drive? Can I transmit all the bits that are sitting on my hard drive to memory, all the characters? And the third one is the latency. How much time do I need to wait until I start receiving my data? These are the 3 important things. Now, if we go back in time to 1956, that was the first commercially available computer that had a hard drive. I think it was IBM. And I put the numbers in there. And now, as a comparison, I now go to today, 2023. So this is what it is now. It's actually quite small, so I need to zoom a little bit. And I wrote again the numbers. And then I tried to do some computations. I always got them wrong. I mean, I still cannot do math, but basically the orders of magnitude are certainly correct. And I got something like this, right? So this is the factor by which each one of the 3 increased. I'm not going to press anything. It's already in there, throughput and latency. So this is by how much the capacity increased, and this is by how much the speed at which we can read it and latency increased. These are the actual numbers. This, in fact, is an absolute catastrophe. I cannot say it better than that, because imagine that we take the comparison with a book, right? Then take me 10 hours to read a book with these numbers. But now if I go 70 years in the future and imagine that what fits in a book and how fast I read will have evolved just like the hard drives actually did evolve, and we go 70 years later, it's going to take me 846 years. Big data, big troubles, right? So this is really a big problem. However, if you realize that by parallelizing and spreading it over 1 billion people, there are surely more than 1 billion people on the planet, right? Then we can get it in 10 hours in parallel. And in fact, that's how we solve that problem. We solve the problem of the discrepancy of the speed at which we can read it and the capacity by parallelizing. And then there's batch processing. It means that we don't process one by one, but in groups of, let's say, 1,000 records at a time. That solves the same thing between throughput and latency. So this is what it means concretely for the architecture of the data centers. That's why we need all of these computers, right? And they exchange, in that case, it's blocks that go between the computers. Physically, we just don't pile up laptops on top of each other in a data center. We have something looking more like this. It's called a rack. And then we have these computers that are just rectangles that we put on top of each other, right? And the idea is that we can store files in there. There's something called Hadoop, the distributed file system. The Google file system was actually the original. And the idea is that we have a hierarchy, and we also store them in blocks just like that. But these blocks are actually more like 100 megabytes. in terms of size, right? But it can go all the way to a petabyte of data, even in the same file. What's nice is that on a machine, you fit roughly 8,000 blocks like this on a single machine. So now you can just prepare all of these buckets of 8,000 each. I'm really exaggerating, but that's the idea. In that example, we spread it over 8 machines, but imagine the same done with billions of blocks, and we do that on 100,000 machines, right? Just so you imagine. This is in fact what's going on in a data center when we analyze the data. Now, what do we store there? And here I'm going to give a big yay to the open information model, XBRL-JSON, XBRL-XML, XBRL-CSV, because this is the right thing to do. We will be able to put them all in this data lake. It's called the data lake, sitting in a data center and analyze petabytes of data that look like this, especially XBRL-JSON. I think is going to be super useful. I also put the other syntaxes for the other languages. Now, how do we analyze this data? Well, of course, we're going to parallelize and batch process, as you can imagine. And here, the real revolution came from Google. It's called MapReduce. We also have it in open source now. The idea is that we can process in parallel like this. Every machine does its stuff on its own blocks, on what is on the machine. Then we have this enormous mess across the data center that we shuffle the data around. There's nothing we can do about that, right? Otherwise, you cannot join the data or interpret it. So there is this shuffling, hopefully as efficient as possible. And then there is a second phase in parallel called the reduce phase. It's incredibly simple, and it's at the same time incredibly powerful because you wouldn't imagine the number of problems you can solve with something that simple. In fact, the Google search engine and many search engines are indexing the internet using that. This is exactly how you download and index the internet, the web, I should say. And then we have newer generations technologies. I'm thinking of Apache Spark that kind of have an additional abstraction layer with an API on top of that. That feels like a Lego game where you can apply all of your transformations on the data. And it's auto-magical. It just runs on the data center and you're just sitting in front of a Jupyter notebook, typing a few lines, and it just works. That's the magic. And on top of that, even better, if you have a language that is aware of the shape. So we have SQL for tables, actually quite useful because you can view it as a fact table, XBRL. But we technically also have MDX, multidimensional expressions for data cubes, and I put a few others for other shapes. Right? So this is the ultimate way of interacting with the data. I'm saying ultimate because on top of that, we might even have ChatGPT and large language models that themselves might interact via these query languages, right? So this is it. This is data independence. If you need just one takeaway message from what I'm telling you today, it's this message, data independence. So important. You want to shield the user from all the complexity. You don't want, in the end, any XBRL user to hear ever about XML. They shouldn't even JSON. It's all about the data cube, slicing, dicing, validating, calculating. This is what it's really about. So if we manage to completely hide the physical layer, this will be wonderful and instrumental to, in fact, scaling up to scales. And maybe I could imagine, I don't know, some sort of, let's be crazy, a global blockchain with all the facts worldwide stored on it. And sharded, of course. Now, the Ethereum blockchain managed to shard, meaning to partition the data. All right, so this is pretty much what I teach to my students, of course, going more into details like that. So we teach relational databases, and big data is a master's level lecture that showed the more recent evolutions, right? I wanted to make a gift to you. Actually, it's a gift for everybody. That's the textbook of the lecture I give at ETH. It's just there for free. There is not even a form to fill with an email address or anything. You can just go there and download it. 400 pages. It's for you if you want to see more about that. It's not even just for computer scientists. I also teach that to non-computer scientists. All right, so with this, I will end my presentation, and I think we even have 10 minutes to spare with questions. Did I do well with that?
Well, thank you. Yes, thank you very much. Any questions from the room?
Hi, I want to sort of in the opposite direction from what you've been discussing here. So one frustration that I have with XBRL is I can't go into Excel, say file open, and load an XBRL document. Does the report packages that you were talking about earlier, does that perhaps address that? And do you see a value in working individually with instance documents, or do you think I'm just wasting my time in the old days and I should be working with big data? Thanks.
I completely agree with you. I completely agree with you. This is why I hate the reporting package, because that's exactly the idea, that you have a file that you don't look inside, you don't even know it's XML, you just click file open and see it. I think Charles Hoffman calls that a semantic spreadsheet. That's exactly the idea. And you can work with individual filings like that. And you can also, big data technologies is for the consuming side, right? How do you analyze petabytes of data worldwide? Then you need to go into big data. But what I tell my students also in the big data lecture is that just because we can do big data doesn't mean that in 80% of the cases, a single machine is enough, right? And you first need to learn to use one machine before you scale. And very often you don't need all of these computers. One is enough. So that's something really important. And just so you're aware of the reason why we go to all the machines, it's really because we cannot read fast enough. That is the main reason. So even I heard, I discussed with some of you earlier, and they mentioned a terabyte of data. It fits on a machine, but that might still be worth doing in a data center because you can parallelize the reading, right? So it's really about the speed at which you read, and you have a bottleneck in reading the data. But for a single filing, I don't expect to have any bottleneck like that, so you don't have to go big data for it. So I fully agree with you. That's
So I have a question about the querying. So you said table link based yay, because it basically does the right way of slicing and dicing of the model that is inherently there. And few people seem to realize that. But for formula, it's a different story. So there's a formula spec that tries to do some kind of querying basically on your instance data. And still what I see is that many parties find that also too difficult and rather just take the table and make a formula exactly on the data points R24 plus, because that's easier to conceptualize. But if you realize it's really a cube, you can realize there is a query language for cubes. So do you have any advice for the formula work group of what would be a good mental model for having a query language that works for cubes but is also easy to comprehend for a human to write?
So I think this is really future looking, is that what I described today was kind of the ideal thing that we should have in the future. It seems to be going in that direction. As I see all the tools that evolve, it's slowly converging in that direction. But it's a long way. And I think, so there are several things to say about that. The first thing that I want to say is that the burden to make it easy to use by the end user, the burden is on the technical people. It's on the developers that have to hide all of that. These are the only ones who should ever read the specifications of XBRL. The end user shouldn't even have to know about all of these details. And this is slowly converging in that direction, but ideally one day we'll have plenty of XBRL processes that look just like a spreadsheet software. That's really also what Charles Hoffman, I hear him saying that a lot. That should be super easy to use. But it's up to us technical people to make it happen, right? We go through this so that nobody else has to. That's the idea. So that would be my advice to the developers.
A question and have a comment. And I think one of the important reasons why we also need to store XBRL information into different forms is also the indexing, right? I think a lot of users don't realize that you cannot just store thousands of reports and then make a query. Otherwise, you'll have to look into each report at a time, right? So a big part of this, I think, is really that you have to prepare for making queries, right? So you agree with that? And
I completely agree. So the idea, so of course I cannot tell you everything I'm doing with my students, but one of the important things that I also teach is we need to look at use cases. It really depends on the use case that you have. What I described here with the large scales is called OLAP. This is for read-intensive queries that really scan through the entire collection. Now, what you're referring to is when you want to look up maybe point queries or small amounts of data, but lost in petabytes of data. This is then not called OLAP, it's called OLTP, right? Online transaction processing. It's a different architecture. And then indeed, we have indices. So what is an index? It's actually super simple to explain. Whoever saw an alphabetical list of words at the end of a book with the pages? right? You look at everybody, right? This is an index. And we build exactly the same thing for databases in order to be able to very efficiently and very quickly, you would be very impressed the speed at which we can retrieve things in a petabyte of data with an index. So I completely agree. It's just that we need to distinguish the use cases. Am I analyzing and aggregating petabytes of data? Or do I want to access just a very specific bunch of data somewhere? And then indeed the indices are exactly useful for this.
Ghislain, have you made or have you seen any progress made in the domain of connecting LLMs, etc., to ontologies and the like? You mentioned that as a different access layer to the data content.
So I think that this is something that is being actively researched. So I'm not an expert in LLMs. I mean, you cannot know everything, right? So I don't know much about large language models or the details of them, or even about graph databases or knowledge bases. However, what I hear a lot coming from academia and people working in the field is that ChatGPT and large language models, they're very good at processing text, right? Predicting the next words, and it's very linear. And so there is a lot of people now who say we really need two parts. We need a part that handles the blah, 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 blah. And we need another part that handles the access to structured data. I hear this a lot. So it seems that I have the feeling there is a slow consensus going in that direction. Now the structured data, maybe it's going to be a knowledge base in the form of a graph database. Maybe it can be more in the form of data cubes, which we might hope will happen with XBRL. So I have the feeling that this is kind of where the conversation is going, also in academia. Does it answer your question? Not quite? Not quite. Maybe I can try to connect you with some people at ETH who are, there is a large language model course at ETH, and there are professors working on exactly that, on trying to extend the large language models with access to actual knowledge bases. Yeah, so I can connect you if you're interested.
So just one question for me, if I may. One of the unique things about XBRL is the ability to have extension taxonomies. And in a lot of projects, preparers submit not only the data, but they can submit their own version of the metadata. Can you say a bit about how you tackle that? I mean, potentially people can do a lot there. They can put in conflicting labels or completely redesign the hypercubes or whatever. How do you tackle that from an analysis point of view?
Mm-hmm. So I would say that it's a bit similar to the discussion that we've had about indices, OLTP versus OLAP, right? And then there is the same conversation around, because this is what it's about open versus closed taxonomy architectures, right, in the end. And so the idea here is that depending on the use case, you might implement your system differently. It means that a system that has a closed taxonomy architecture will be implemented differently than a system who had an open taxonomy architecture. So it doesn't change anything to data independence. It's just the idea that this is really this idea that if you have a UI that allows you to build new metadata on the fly, new concepts and so on, you will have to also implement the physical layer to make it happen. But the benefit, it's always a cost-benefit thing in IT, right? If you have a new feature, it has a cost. If you drop the feature, then you get more performance, right? So of course, if the users cannot create metadata, then you can start making assumptions in the implementation and then fine-tune things to make them even faster. So all of these considerations, open or closed, this just has an impact on the software design. It doesn't change anything to the fact that the burden is on us technical people to make this easy to the user.
I sense a theme here. Okay, I'd like to thank Ghislain very much for that
Thank you.
very engaging presentation. Thank you.